So, in this lecture we are going to tell you about the symmetry property of a two port network, under what condition we call this two port network to be symmetric, and which will be followed by the series, parallel and cascade connection of two port network. So, let us see what does that symmetry means. You recall that in a two port network, we have drawn this figure several times, but this is V 1, this is I 1 and this is say V 2, this is I 2. And we are writing sometimes capital, sometimes this one, because they may be in time domain, they may be in Laplace domain, they may be in frequency domain, it does not matter. But the point is we have seen that the if this two port network is expressed in terms of Z matrix, it will be that is the input voltage and output voltage can be written as Z 11 I 1. Okay, we are writing capital letters. Let me write that. So, these are I 2, this is I 1, and we have seen that V 1 is V 1 is equal to Z 11 I 1 plus Z 12 I 2. And V 2 is equal to Z 21 I 1 plus Z 22 I 2. We have seen that if this network, two port network is when this two port network will be which property that is reciprocal. If this two port network is reciprocal, we have seen that Z 12 should be equal to Z 21, that we have established earlier for reciprocity, Similarly, whether there exists any condition under which this matrix will be symmetrical, this two port network will be symmetrical. Okay. A two port network is said to be symmetrical if these two elements are same, these two elements are same. For an impedance matrix, if Z 11 is equal to Z 12, then it is said to be symmetrical. Z 22 symmetric. Now, what is Z 11? Z 11 is Z 11 is equal to V 1 by I 1 with I 2 equal to 0. That is the driving point impedance of the network looking from port 1 and driving point impedance of this two port network looking from port 2, that is V 2 by I 2 with I 1 equal to 0. If these two are same, if these two ratios are same under the condition that I 2 equal to 0 here and I 1 equal to, that is secondary is open circuit, driving point impedances are same, then it is this one. So, naturally this is the condition for reciprocity, that is no matter in which form you describe the two port network, that is in short circuit admittance matrix or ABCD parameters or H parameters, whatever you do, this is the thing. driving V 1 by I 1 with I 2 equal to 0 you have to find out, and V 2 by I 2 with I 1 equal to 0 you find out, and for impedance matrix this one it happens to be Z 1 1 equal to Z 2 2. So, the thing is this thing I have to calculate, that is V 1 by I 1 with I 2 equal to 0 should be equated to V 2 by I 2 with I 1 equal to 0. So, let us see what happens if it is admittance parameters if we describe the function. So, for Y matrix, so it will be equal to I 1 and I 2, we know it is equal to Y 1 1 V 1 plus Y 1 2 V 2, and this will be equal to Y 2 1 V 1 plus Y 2 2 V 2 is not. Therefore, to find out V 1 by I 1 with I 2 equal to 0, I have to calculate this under this condition, that is if we want to find out V 1 by I 1 with I 2 equal to 0, first I will find out this. So, this equation then will give me for this condition I 2 being 0, the second equation will give you 0 is equal to Y 2 1 V 1 plus Y 2 2 V 2. This is the second equation will give me this, because I 2 equal to 0, and the first equation will give you I 1 is equal to Y 1 1 V 1 plus Y 1 2 V 2. My objective is to calculate V 1 by I 1. So, V 1 is there, I 1 is there, but here is a V 2, and this V 2 I will calculate from this first equation as Y 2 is equal to minus Y 2 1 by Y 2 2 into V 1, and this I will substitute here, or I will say I 1 is equal to Y 1 1 V 1, and then for V 2 you substitute this, and this will become minus Y 2 1 Y 1 2 by Y 2 2 into V 1, and this will be equal to Y 1 1 Y 2 2 minus Y 2 1 Y 1 2 by Y 2 2 into V 1. Therefore, you can easily see that V 1 by I 1 with the condition I 2 equal to 0 will be equal to Y 2 2 divided by Y 1 1 Y 2 2 minus Y 2 1 Y 1 2. This we keep. Then I calculate V 2 by I 2. This of course is obvious. Hopefully, I will get Y 2 2 is equal to Y 1 1. Why not? Driving point admittance should be same. So, anyway, I will do this very quickly. So, V 2 by I 2 I want to find out with the condition I 1 equal to 0. So, from the first equation I will get 0 is equal to Y 1 1 V 1 plus Y 1 2 V 2. This is the first equation, and second equation is I 2 is equal to Y 2 1 V 1 plus Y 2 2 V 2. This is the second equation, and I want to find out V 2 by I 2. So, V 1 I will substitute from the first equation. So, it will be V 1 will be equal to minus Y 1 2 by Y 1 1, is not, into V 1 into V 2 and plus y 2 to V 2. So, this will be then once again y 2 2 minus y 2 1 y 1 2 by y 1 1 into V 2. So, V 2 by I 2, this is what I have to find out with I 1 equal to 0 will be simply y 1 1 divided by the same thing y 1 1 y 2 2 minus y 2 1 y 1 2 this, and these two, if you equate these two, the conclusion is y 1 1 should be equal to also y 2 2, that is driving point admittances should be also same. So, this is the condition for a two port network which represented in the form of admittance matrix, this condition should be satisfied. Now, let us do it for H matrix, what condition it will satisfy in order that it becomes a symmetric matrix. Therefore, you recall that this H matrix equation is V 1 I 2 is equal to, is not, H 1 1 I 1 plus H 1 2 V 2, and this is H 2 1 I 1 plus H 2 2 V 2. So, this is the two port network plus minus, these are the conventions which we should not break to find out anything. So, this is V 2, this is I 2. Suppose these relationships are expressed in terms of the H parameters, then we know to test the symmetry we have to calculate this V 1 by I 1 with I 2 equal to 0 and V 2 by I 2 with I 1 equal to 0, and I will equate them to get the desired condition. That is what I have to do. So, in this case the first one if you take, that is I want to calculate V 1 by I 1 with I 2 equal to 0, means that I will keep the secondary open circuited, I will apply some voltage here. Therefore, from the first equation you will get V 1 is equal to H 1 1 I 1 plus H 1 2 into V 2, that you will get, is it? And from the second equation you will get 0 is equal to H 2 1 I 1 plus H 2 2 into V 2. This is from this equation, I will get this. And I want to calculate V 1 by I 1. So, this V 2 I will express in terms of I 1. Therefore, here I will write V 2 is nothing but minus H 2 1 by H 2 2 into I 1, and this I will put it here. Then it will be V 1 is equal to H 1 1 I 1 plus H 1 2 into V 2, that means minus H 1 2 H 2 1 by H 2 2 and this into I 1, it will be like this. Therefore, we get V 1 by I 1 with the condition that I 2 equal to 0, output port open circuited, you will get H 1 1 H 2 2 minus H 1 2 H 2 1 divided by H 2 2. This is what you will get. I will call this is equation 1. Similarly, I will calculate now calculate V 2 by I 2 with the condition I 1 equal to 0, that is primary side, that is input side is open circuited. So, that I 1 0, you excite it with a voltage V 2 and record these quantities. Then you will get from the first equation, since I 1 is equal to 0, V 1 will be equal to H 1 1 into 0, I 1 0 plus H 1 2 into V 2, and this is simply H 1 2 V 2. I will get the from the first equation, and from the second equation you will get I 2 is equal to this equation. I am writing now I 2 is equal to H 2 1 into 0, I 1 is 0 plus H 2 2 into V 2. This is what I will get, and this is equal to H 2 2 into V 2. I have to calculate V 2 by I 2, is not V 2 by I 2 I have to calculate. Everything is fine here. So, V 2 by I 2 from the second equation itself I get that V 2 by I 2 from this equation is 1 over H 2 2. Therefore, the condition this is with I 1 equal to 0, and I know that for this two port network to be symmetric, this one and this one, that is this ratio, this and this, they must be equal. Therefore, the condition is 1 over H 2 2 is equal to H 1 1 H 2 2 minus H 1 2 H 2 1 divided by H 2 2, or I will say this H 2 2 cancels out, provided it is not equal to 0. I mean H 2 2 cannot be 0. Therefore, the condition is H 1 1 H 2 2 minus H 1 2 H 2 1, this must be equal to 1, or I will simply say the determinant of this matrix H 1 1 H 1 2 H 2 1 H 2 2, this must be equal to 1 determinant. This determinant, if it is 1, I am sure it is a symmetric two port network. Is that clear? Now, we will see what about ABCD parameters, how it will, what is the condition when a two port network, same two port network is expressed in terms of ABCD parameters, then if that network is to be symmetric, what is the condition? So, let us do it once again. So, a network is like this. Suppose this network is expressed in terms of T parameters or ABCD parameters. This is this thing plus minus V 1, this is I 1, is not, and for ABCD parameters what I have assumed earlier, that is we will keep it, it is like this. This is the convention for ABCD parameters or transmission line parameters, and then we know this input voltage and current, is not, it is expressed in terms of A V 2 plus B I 2, and this is equal to C V 2 plus D I 2. These are the condition. But what if this network is to be symmetric, if this two port network if this one is to be symmetric, I will demand that V 1 by I 1 with I 2 is equal to 0 is with I 2 equal to 0. This is open circuited V 1 by I 1, driving point impedance of this network. This should be equal to V 2 I 1 equal to 0, is not? But what should I write here? That is what I am telling. I must write minus I 2. The driving point admittance is this. This you must understand very clearly. So, in this case, because of this surprise change in the direction of I 2 while describing an ABCD parameters, this is I have to do. But so far as driving point admittance, that is the impedance is concerned, Z22. So, the current is to be reversed, because for Z parameters it enters. You have got the point. Now, this is the thing. Therefore, let us first calculate, first do this V 1 by I 1 with I 2 equal to 0, this thing. So, what we get? With I 2 equal to 0, V 1 from the first equation, these are the fundamental equation for general case. Okay. So, V 1 is equal to A V 2 plus 0, I am not writing that from this first equation, I 2 is equal to 0. From the second equation, for the same condition, you will get I 1 is equal to C V 2, you know, that is what I will get. Therefore, the ratio V 1, you just divide these two and you get your desired result, that is I wanted to calculate V 1 by I 1 with I 2 equal to 0, then I will get it as this by this, which will be equal to A by C. I keep this result with me. Now, I have to calculate V 2 by minus I 2. Okay. For the second, now I have to calculate V 2 divided by minus I 2 with I 1 equal to 0, I have to calculate it. You know. Now, to calculate that, first let us see from these equations what we get. We get that I 1 equal to 0, and so the first equation is V 1 is equal to A V 2 plus B I 2, that is there, and from the second equation I will get this equation I 1 equal to 0 is equal to C V 2 plus D I 2. But I have to calculate V 2 by I 2, and V 2 by I 2 can be calculated from this itself, is not? First equation is not necessary. If wrong, tell me. So, this is fine. Therefore, I will say that C V 2 is equal to minus D I 2, or I will say that V 2 by minus I 2 is equal to D by C. This is the thing I will get. And so, these two should be equated, this and this one should be equated. So, what will be the result? Therefore, to be symmetric, these two should be same, that is A by C should be equal to D by C, or A equal to D is the condition. Is that clear? A equal to D will be the condition. Therefore, for ABCD parameters, just looking at the values of A, B and C and D, we can conclude whether this we can say about this two port network whether it is symmetric or not, that is the thing. So, for a two port network to be symmetric, if it is expressed in terms of impedance matrix, Z11 should be equal to Z22, Y11 should be equal to Y22, and if it is expressed in terms of H parameters, then the determinant of H matrix should be equal to 1, and if it is expressed in terms of ABCD or T parameters, then A and D should be equal. So, this is about the symmetry. In the same way, we have found out the conditions for a network to be reciprocal. Like that, several conditions we have found out. Now, what I will do is this. So, this is the thing. Okay. Understood? Therefore, we will now say something about series parallel connection of various two ports network. Okay. Series connection first. Series connection. These are very simple stuff, not tough at all. Series connection of two ports of two port networks. Now, suppose you have got two port networks. It can be extended to 3 two port networks as well. Only for 2, if we understand, we know what to do with others. So, this is 1 plus minus, this is V 1, this is I 1, and this is the network plus minus V 2 and this is I 2. Now, so this is network 1. Take another network. So, N 1 two port network, another network N 2. It will also have a pair of terminals here in the input port and also in the output port. Let this be called I 1 dashed and its input voltage be called V 1 dashed, and this voltage is plus minus V 2 dashed and this is I 2 dashed. First of all, what do I mean by series connection? When we say that these two port networks are in series, it means that the input ports will be in series connected, that is this connection I will show with a red color. It is connected like this, and these two are the total input of this. Similarly, on the output side, you connect them in series and treat these two as output terminals. Now, obviously, you can easily see that suppose I am expressing these networks N 1 and N 2 in terms of impedance parameters, suppose. So, what we will be getting? So far as network for N 1, network 1, I will get V 1, V 2 is equal to Z 11 I 1 plus Z 12 I 2, that is what I will get, and this one I will get is Z 21 I 1 plus Z 22 into I 2. This is for network 1. For network 2, what I will get? So far as this one is concerned, I will say all the parameters will be replaced by dashed here. So, V 1 dashed is the input voltage for N 2 input port voltage, and V 2 dashed, these are the input voltages, and they are expressed in terms of Z 11 dashed I 1 for this network. Parameter value may be different, we do not know I 2. So, I 1 dashed, I 2 dashed. Similarly, Z 2 1 dashed, I 1 dashed plus Z 2 2 dashed, I 2 dashed. This will be the thing. Now, this if you, so this is equation 1, this is equation 2, 3, 4. Okay. This is how I have written it. But now you see that because these two ports are series connected, this I 1 dashed is nothing but I 1 itself, is not? This I 1 and I 1 dashed, they are same. Therefore, these two equations can be similarly. So, important thing to note is I 1 dashed is equal to I 1 and I 2 dashed is equal to I 2. So, these two currents must be same. If that be the case, then V 1 dashed is equal to this 3 and 4, 3 and 4. I am rewriting after knowing this. I will say it is nothing but Z 11 dashed I 1 plus Z 12 dashed into I 2 dashed, and the fourth equation, that is this one, will then be Z 21 dashed I 1 plus Z 22 dashed into I 2. I am sorry, this dash goes because I am using this relation. So, this is 5 and 6, same 3 and 4 equation with this knowledge 5 and 6 here. Now, what you do? You add that is equation 1 and 5 you add. If you add 1 and 5, you will get left hand side, you will get V 1 plus V 2 dashed. This equation and this equation I am adding. So, V 1 plus V 2 dashed, it will be simply Z 11 plus Z 11 dashed into I 1, this term and this term added up. Similarly, this term and this term added up. So, plus of Z 12 plus Z 12 dashed into I 2, that is what I will get. Is not? Have I written something wrong? Yeah, I have written. So, this is V 1 plus V 1 dashed. So, V 1 plus V 1 dashed. Similarly, you add 1 plus 5 I have added. Now, I will add 2 plus 6, add 2 plus 6. If you add 2 plus 6, you will get V 2 plus V 2 dashed to be equal to Z 2 1 plus Z 2 1 dashed into I 1 plus Z 2 2 plus Z 2 dashed Z 2 2 dashed into I 2. Z 2 2 plus Z 2 dashed, is not? This is what I will get. Now, this whole network, this two series network can be thought of a single two port network. After knowing these two equations, I will say that this is the equivalent two port network is this. These two are series connected, where the input voltage, you see what is the potential of this. These are the input ports can be considered to be this series connected two port networks, and these two are output ports of these two series connected networks. Therefore, between these 2 points the voltage is how much? V 1 dash plus V 1, that is the input voltage, V 1 plus V 1 dash. What is the current? I 1, and this side it can be thought of V 2 plus V 2 dash is the voltage between this output port. So, V 2 plus V 2 dash, and what is this current? I 2. So, equivalent. So, therefore, if two or several two port networks are connected in series, and then the overall equivalent two port network representation will be input port voltages will be sum of all the voltages here. Input currents are same I 1, it is I 2, but the interesting thing is the impedance matrix of this two port network will be sum of this impedance values of this network and this network. That is the overall impedance matrix, overall impedance matrix is nothing but Z 1 1 Z 1 2, Z 2 1 Z 2 2 plus Z 1 1 dashed, Z 1 2 dashed, Z 2 1 dashed, Z 2 2 dashed, is not. Then only you will get term by term addition. These elements will be Z 1 1 plus Z 1 1 dashed. This element will be Z 1 2 plus Z 1 2 dashed. This will be Z 2 1 plus Z 2 1 dashed, and this will be Z 2 2 plus Z 2 2 dashed. Got the point? Obviously, you can easily now feel any two port network can be represented in several ways, either in terms of Z parameters, ABCD parameters, Y parameters, like that. But if they are series connected, I can find out the overall, I can replace this series connected two port network by a single two port network, whose parameters values, if you know the impedance matrix separately here and there, you can just add them and get it, very simple. Perhaps in series connected two port networks, it will be easier if you represented it in the form of Z matrix. What it will turn out to be, if it is admittance or H parameter, we can find it out, but it will be complicated. After all, after you have found out this one, you always know how to translate this parameter value in terms of ABCD or Y parameters or so on, or H parameters, because each one of this representation is related with others, provided determinant is not equal to 0, all these things. We will continue our discussion with this in the next class. Thank you.